Hello everybody, today I'm going to present the direct numerical simulation and parametric study of the noise generated from particle dispersion in decaying homogeneous isotropic turbulent flow. My name is Wang and my advisor is Stephen Miller. First, let me acknowledge the funding agency. This research is supported by Florida Space Research Initiative under the project of prediction and reduction of noise from rockets. The outline of this presentation includes 4 parts. The introduction, the numerical method, which covers the governing equations and the acoustic analogies, and then the result and the discussion, which covers the problem definition, the root mean square acoustic pressure, and the root mean square acoustic pressure of different source terms. And last but not least, the summary and future work. First, the introduction section, we know that there are a number of decaying isotropic turbulence laden with solid particles in many in many studies, and these 2 figures are from the studies of Ferrante and Agonbash. We can see from these figures that the two-way coupling of gas and particles modify the turbulence in terms of both the decay rate of the total kinetic energy of turbulence and also its spectral component. But an aspect that researchers often not focus on is the physical parameters of the particles and how they change the noise generation in the far field. So we want to keep focus on that, and we use a workflow of hybrid DNS and acoustic analogy for the far field noise, and it is in different stages, performs in these 3 stages. First of all, we perform a DNS simulation using CFD solvers coupled with point particle solvers, and in a Euler-Lagrangian reference framework. And then in the intermediate aerodynamic stage, we obtain the time-dependent flow field, and through that we can do a acoustic analogy to find the far field noise using acoustic solvers that we developed, and then we can directly analyze the source statistics in the source region. For the governing equations of the CFD solver, we use a Navier-Stokes equation that is coupled with particle sources through this Q term here, which is the coupling term, and the source from the particles are given from the evolution equation. By solving the evolution equation of the particles, the location, the velocity, and the temperature of the particles of each particles are tracked in time and involved in time. And the numerical solver we use is called rock fluid MP, and the particle solver we use is called rock part, that is built-in module of rock fluid. And for the acoustic analogies, we use one derived by given by Crighton and Ffowcs Williams. The inhomogeneous wave equation is given here, and we can see there are 3 source terms in the right-hand side of the equation. There are the monopole sources, which is just a material derivative of this function of volume fraction of the particles, the alpha here, and this term, source term, represent the effect of volume fraction of the particles on the noise generation, and the dipole source is consists of the drag force that particles impose on the gas, and also the time rate change of the momentum due to the particle volume effect. And the quadrupole sources is just a light yield stress tensor that represent the noise generated aerodynamically. And for this acoustic analogy, we solve it using a free space Green's function, and the full solution is given here. and we implement this equation into our CFD solver and output the acoustic pressure in time associated with these three source terms, and we can individually analyze them in the following slices. For the DNS simulations, we want to study the effect of total number of particles and the diameter of the particles on the generated noise. So we have these two parameters listed in this table, and we perform the DNS of each combination of these two parameters, and we perform those. We perform a total of 50 cases, and it is under two different initial conditions of the gas. And for the initial conditions, we prescribe the initial condition using Kirchner's method. Through this method, the initial velocity field is divergence-free and isotropic. And the turbulent kinetic energy spectrum, for the initial condition, we use Schumann and Patterson's. And here the U0 star is the initial velocity scale, and we use two different initial velocity scale for the simulations. As a result, we compute the PRMS root mean square acoustic pressure, and we compare that with the changing number of particles on the left figure and with the particle diameters on the right figure. And the marked legend is for another the other parameters. So in the left figure is the diameter of the particles. In the right figure is the total number of particles. And the solid line is the cases with lower initial velocity scale at 0.05, and the dotted line is the dotted line represent the higher initial velocity scale of 0.20. And we can see from these two figures that the acoustic pressure for different cases just collapse for different number of particles, and the diameter of particles just collapse into 1 point, and that is the gas case, also the gas case PRMS. So in this region here, and for the tiny particle of 10 micron, we can see that the impact of the particles are really minimum. And as a general trend, we can see that acoustic pressure increases with increasing number and the diameter of the particles. And the initial condition is only significant at low number of particles, and for smaller particles, we can see that for different initial condition there is a gap here, but not here when the particle diameters are large, over 100 micron, and when the number of particles are large. And we also plot PRMS versus the volume fraction, since we think the volume fraction is a good parameter to study. It includes both the number of particles and the diameter of the particles, and it also appears in the Crighton and Ffowcs Williams acoustic analogy. And this figure is very interesting. We can see that the changing of volume fraction doesn't impact the flow, and when it is lower than 10 to the power of -6. And if we fitted a trend line here, the PRMS goes as volume fraction of power 0.01 and 0.15 for the U0 of 0.05 and 0.2 respectively, and that is really minimum influence on the acoustic pressure. And here we can see that the initial velocity actually makes the difference, and we can infer from that the turbulence actually dominates for the acoustic pressure when the volume fraction is lower than 10 to the power of -7. But when the volume fraction increases beyond, especially beyond 10 to the power of -6, we can see that all the cases collapse, all the PRMS collapse on a straight line, and it scales strongly with volume fraction, and actually it scales with the volume fraction raised to power of 2.4. It shows that in the high volume fraction region, the cases, the PRMS, the particle dynamics really dominate the noise generation process. And as a step further, we want to look at the PRMS, the acoustic pressure of associated with each terms. First of all, let's see the acoustic pressure associated with lattice stress tensor that just represent the noise generated by the turbulence. Here we can see that the number of particles and the particle diameters don't really impact strongly on the PRMS, and here the most significant impact comes from the initial velocity field, the U0 here. And if we plot the PRMS versus the volume fraction, we can see that largely the RMS doesn't change with respect to the volume fraction, and it actually decreases at around volume fraction around 10 to the power of -5, and increases when the volume fraction becomes larger than that. It shows that the turbulence actually is changed due to the strong two-way coupling of turbulence and the particles. And next, let's look at the acoustic pressure of the monopole sources. And in the interest of time, we do not really plot the change of PRMS versus the dipole source, but the general trend is very similar to the with the monopole source. So let's look at the monopole sources. So here it's very clear that the effect of the number of particles and the diameter of particles are independent of each other, and we can see really the scaling doesn't really change much if we see this each lines and we see this each curves here. And when we plot them against the volume fraction, it is very interesting. And this figure, we plot both the monopole source and the dipole source, with the monopole source being the full mark, the solid mark, and the dipole source being the empty mark. And this green marks just compare shows the quadruple sources. And here, if we fitted a trend line, the monopole source goes as a volume fraction raised to the 2.5 power, and the dipole source goes as a volume fraction raised to 1.74 power. And one thing to note here is that the monopole source and the dipole source is really comparable in their magnitude, and they're dominant. They are the most dominant ensemble source for volume fraction greater than 10 to the power of -6, and the quadruple source actually is the most dominant noise source for for volume fraction 10 to the power of -7 and below. So as a quick summary, we perform DNS on isotropic turbulence laden with particles in 50 cases with varying total number and the diameter of the particles. And we use Crighton and Ffowcs Williams acoustic technology for two-phase flow to investigate the different noise source and the acoustic pressure associated with them. And we found that the quadruple source dominant for low volume fraction, but the monopole and dipole source are more dominant in the higher volume fraction, and the acoustic pressure scales as 2.5 power of the initial volume fraction. And as a next step, we want to utilize the linear forcing and study the stationary isotropic turbulence laden with particles, so we can look at the spectral component of the noise of each source terms. And with that, I will thank you everybody for your time, and I'm open to any questions.